Lesson 81 we'll be talking about finding graphical solutions to a set of simultaneous equations, and then we'll also describe what inconsistent and dependent equations are. Now, when you first learned how to solve a system of simultaneous equations, that was way back in lesson 54, and when I described how to do that, I used the example of changing the equations to equations of a line and graphing them and showing that when you solve a system of simultaneous equations, you're actually solving for where those two lines intersect on an xy axis. Now in this lesson, that's what they want you to do, is to solve this system of simultaneous equations by graphing them instead of using the substitution or the elimination method. What I would do if I were you, though, is just to check your work, is go ahead and use the substitution or elimination method, because that's more accurate than making a graph. So like on this example here, let's just go ahead and use the elimination method. It'd be real easy because we have opposites of x there and they would cancel out. So add the y's together and we have 2y is equal to -2. So y equals -1. And then if y is -1, let's just substitute back into the top equation. We'd have -1 equals x plus 2. And so x would be equal to -3. And so our ordered pair is going to be not -1 first, -3 first, -3, comma, -1. That will be our ordered pair. Well, let's see if we're right or not. Let's go ahead and graph it. Now you don't have to use the substitution or elimination method to check your work. I mean, it takes a little extra time, but it doesn't hurt to be careful before you get your actual answer, or say that that is your actual answer. So let's go ahead and graph these two lines. Let's graph the first one, y equals x plus 2. So that means we would start at +2 with our y-intercept, and our slope is 1, so that means the change in y is 1, the change in x is 1. And so we go up 1 to the right 1, make a point. Up 1 to the right 1, make a point. Up 1 to the right 1, make a point, and that's plenty. Let's go down 1 and to the left 1, make one more, and then we can draw our line through that. Now let's go ahead and graph the next one, y equals -x minus 4. And so on this one, our y-intercept is at -4. So right here, our slope is -1. So we can say the change in y is -1, the change in x is +1. And so we would go down 1 to the right 1, down 1 to the right 1. We could also go from the y-intercept up 1 and to the left 1, right? And that would continue our pattern there. Let's go up 1 to the left one more. And now let's draw a line through that. Okay, now we said that our lines would intersect at -3, comma, -1. And so look at what they did here. Right there. And that's not quite perfect. It's a little bit past -3, but it's close enough. You can assume that usually when you do these problems that you have whole number answers for your points, or integer answers anyway, for where they intersect. So remember, when you do a graph, though, when you try to find the graphical solution, it's usually not as accurate as doing substitution or elimination, mainly because it's just hard to draw a line perfectly. If you had a perfect piece of graph paper and then you did ruler lines exactly like you needed to, then you might get pretty close. But like what I'm doing here, I'm just putting some tick marks down. I'm not even estimating, or I don't have a ruler or anything to mark the distance between my tick marks, so they're not all exactly the same. And so that tends to make my intersection a little bit off from what it actually is. But that is close enough to tell us that -3, comma, -1 is the correct answer. Let's do another one. We have two equations here, y equals -x and x equals 2. Now that doesn't really look like a system of equations like we're used to, but nevertheless those are both equations for lines, right? And so unless they're parallel, they should intersect somewhere. We can go ahead and estimate where they will intersect. X equals 2. Remember, all you do is draw a line through the x-axis at 2, but that's its value for x as well. It has to be 2. And then we could substitute that into the first equation, and so y would be negative 2. So we should expect these two lines to intersect at 2, negative 2. Let's go ahead and draw an xy axis. And let's do the first line, y equals negative x. So think of your formula, y equals mx plus b. If there's no constant term there, that means b is 0, so our y-intercept is 0. And then y equals negative x. The slope is negative 1, and so we think of that as minus 1 over 1. Our change in y is negative 1 and to the right 1. So we start at 0 and make some points, down 1 to the right 1, down 1 to the right 1 again. I'll go up 1 and to the left 1 as well. That still keeps me in line with that negative slope. And so there it is. And then x equals 2, like we said earlier, we just draw a line straight through x equals 2. Okay, now look at that point of intersection there. And that is pretty much right at 2, negative 2. So that is correct. That's the point of intersection, 2, negative 2. So when we solve a system of linear equations simultaneously, that means we solve for where they intersect if we graph them on an xy coordinate system. Let's go on to the second part of this lesson on 81B and C on inconsistent and dependent equations. Now if I had this system of simultaneous equations, y equals x plus 2 and y equals x minus 3, if I tried to graph that, there would be no solution. Why do you think that is? Well, look at them. They both have the same slope, and so lines that have the same slope, they're parallel to each other. They never intersect. So that set right there would be considered a set of inconsistent equations because the slopes are the same. So that's just something to remember. That's just a definition of a type of system of equations. They're called inconsistent if the slopes are the same. Look at this system of simultaneous equations. 3y equals 3x plus 6, y equals x plus 2. Now, at first glance, you might think that the slopes are different. But if we divided that top equation through by 3 everywhere, it would be the same as the bottom one. Everything would be the same. The slope and the y-intercept would be the same. So we call those kinds of equations dependent equations. So that's just another definition for systems of equations. They're considered dependent if m, which is the slope, and b, which is the y-intercept, if those are the same in both equations. So sometimes they may be asking you in the problem set to tell you if they're inconsistent or dependent types of equations. They're inconsistent if the slopes are the same. They're dependent if they're exactly the same equations, and sometimes you'll have to factor something out or divide through to see for sure if they're the same or not. Now, there's another type of equation or system of equations, and that's called a consistent set of equations, and they're consistent if they intersect at some point. So like practice problem A and B, those would be considered consistent equations. So if they intersect, they are considered consistent. Let's do a practice problem relating to these types of equations, consistent, inconsistent, and dependent. Look at practice problem C. I want you to tell me if that system of equations there is a consistent, inconsistent, or dependent set of equations. Well, the first thing you should do on a set like that is to rearrange them and solve them for y. Put them in the standard form of an equation of a line. So let's take the first equation, and we would say 2y we'll just move the x over in our head. 2y equals negative x plus 1. And then we would divide every term by 2, and we would get y is equal to negative 1/2 x plus 1/2. Now, the second equation, let's go ahead and rearrange that as well. We'd have 4y is equal to negative 2x plus 11. And then if we divide every term by 4, we'd have y equals negative 2 over 4, or just negative 1 over 2 times x plus 11 over 4. So now let's just circle our two rearranged equations that we have in standard form now. Here's one of them, and here's the other one. And look at those. If the slopes are the same and the y-intercepts are different, then it's considered inconsistent, and that's what we have there. They're consistent if they intersect. If they intersect, their slopes are different. So they have the same slope, so we know they're not consistent. Dependent would be slopes and intercepts the same, but that's not true either. So this is an inconsistent set. Basically, they're parallel. That's just the name given to a set of linear equations like that when they have the same slope. They're called inconsistent. They never intersect. Okay, well that's all for lesson 81.